Okay, thanks for joining me for tutorial 8. In today's tutorial, we're going to go over multiple comparisons and do some example problems. So before we get started, I just wanted to quickly review the steps of hypothesis testing because these apply to all tests covered in the course. So first, we always start by stating the null and alternative hypotheses. We then ask if our explanatory and outcome variables are qualitative or quantitative. If one of these is qualitative, we then ask how many groups are being compared, and if these are paired or independent groups. At this point, we should have a pretty good idea about the parametric tests that we should conduct, but we first need to make sure that our assumptions for our parametric test are met. And if they're not met, we should conduct the non-parametric alternative to that test. We then perform our test and determine whether we should reject or fail to reject the null hypothesis. In the last tutorial, we introduced one-way ANOVA. We talked about how we follow all of the previous steps for hypothesis testing to conduct one-way ANOVA. But we also showed that this test only allows us to conclude either that we don't have enough evidence to believe that there is a difference in means, or we have evidence to believe that at least one group mean differs from the others. But we cannot conclude from ANOVA alone which group mean differs. To determine which group or groups differ, you could do multiple t-tests, but the problem with this is that it would take a lot of time to compare the different groups. So say if you had 6 groups, you would have a total of 15 tests. But the biggest concern is that if you were to compare all groups using multiple t-tests, you increase your risk of a type 1 error, or concluding that there are significant differences when these don't actually exist in reality. So if we were to do multiple t-tests, we have a greater likelihood of making at least one type 1 error, or falsely rejecting the null hypothesis at least once. For example, if you had 3 groups being compared, the total number of possible pairwise tests is calculated by multiplying the number of groups times the number of groups minus 1 and dividing this by 2. This would give you a total of 3 possible pairwise tests that each have a significance level of 0.05. In other words, the probability of a type 1 error with each of these tests is 0.05 or 5%. This means that the probability of not making a false rejection for each of the 3 t-tests on their own is 0.95 or 95%. But the probability of not making a false rejection on any of these tests is 0.95 to the power of 3, which equals 0.86. In other words, over the 3 tests we conduct, there is only an 86% chance that we have not made a false rejection for any of these tests, assuming that the null is true. Or stating this differently, there is a 14% chance that we have made at least one type 1 error or false rejection. If we compare 4 groups, there is a 26% chance that we've made at least one false rejection. If we compare 5 groups, there is a 40% chance that we have made at least one false rejection. This is, of course, much higher than our original 5% chance with a single t-test. So this is why we need to adjust for multiple comparisons. There's a good discussion and example of this in the module notes on page 33, as well as how we can correct for this using a method such as Bonferroni's method on pages 48 to 52. So if we conduct one-way ANOVA and reject the null hypothesis and have evidence to suggest that at least one group mean differs, we then need to do additional tests to determine which groups significantly differ. But as I mentioned, we can't just conduct multiple t-tests to do this, because then our likelihood of a type 1 error will increase. We must instead use a method that allows us to adjust for this problem of multiple comparisons. Some methods that we can use to adjust for multiple comparisons are Bonferroni's Tukey's, or Dunnett's tests. We won't go into too much detail on Tukey's or Dunnett's, but I'll go over the Bonferroni method because these tests are pretty similar, so then you'll be able to understand the general concepts behind the other two. So Bonferroni's proposal to address the problem of an increased likelihood of a type 1 error was to use an adjusted significance level. This significance level is determined by taking your significance level and dividing it by the number of possible pairwise tests. We determine the number of possible pairwise tests with the formula k times k minus 1 divided by 2, which I've said means the number of groups times the number of groups minus 1 divided by 2. So if we had 4 groups, the number of possible pairwise tests would be 4 times 3 divided by 2, which equals 6. So our adjusted significance level would be 0.05 divided by 6, which equals 0.0125. We use the same procedure for conducting hypothesis tests and confidence intervals for the difference of two population means, except that we use the more stringent significance level to adjust for the fact that we're making multiple comparisons. And we use the variance within for the pooled variance, and our degrees of freedom is the sample size minus the number of groups. So you can see that compared to our calculation of confidence intervals, when comparing the differences of two population means, we use the same formula, except our t uses our adjusted significance level, our degrees of freedom is the sample size minus the number of groups, and instead of the pooled variance, we use the within group variation. And when conducting a hypothesis test for pairwise tests, you reject the null hypothesis if your p-value is less than your adjusted significance level. So let's try an example problem. A research study was conducted to examine the clinical efficacy of a new antidepressant. Depressed patients were randomly and independently assigned to one of 3 groups: a placebo group, a group that received a low dose of the drug, and a group that received a moderate dose of the drug. After 4 weeks of treatment, the patients completed the Beck Depression Inventory. The higher the score, the more depressed the patient. The researchers wanted to know if the drug alleviates depression and if they should be recommending a particular dose. So we go through all of the steps for a hypothesis test to answer the question. First, we want to state our null and alternative hypotheses and determine the characteristics of our outcome and explanatory variables. So are they qualitative or quantitative? Are paired or independent groups in the explanatory variable being compared? And then we'll determine if we should do a parametric or non-parametric test. The null hypothesis is that there is no difference in the mean BDI score between the 3 levels of the drug groups. The alternative hypothesis is that at least one mean BDI score of the 3 levels of drug groups will be different. So our outcome of BDI is continuous, and 3 groups are being compared in our explanatory variable: the placebo, the low dose, and the moderate groups. Since these groups have completely different people, they are independent. So when comparing 3 independent groups with our explanatory variable, and our outcome is quantitative, the parametric test is ANOVA. But we need to check that our data meets the assumptions for ANOVA first. So we know the sample was selected through a simple random sample, and that the observations within groups are independent, and the different treatments being compared are independent. The next assumption is that each group set of observed values comes from a normal distribution. We can assume that this is met if the sample size of each group is large, so greater than 20 per group as a rule of thumb. But this information isn't provided in the study description here, so we need to look at a box plot, histogram, or QQ plot. And the final assumption for ANOVA is that the variation for each group is approximately equal. And so we can check this by comparing the standard deviations provided or by looking at side-by-side box plots. So let's see if our data meets the assumptions of normality and equal variances. By looking at the box plots provided, we can see that the observations in each group seem to approximate a normal distribution. The interquartile range and range are fairly equal around the median in each of the groups. And if we compare the box plots for each group, the variation seems to be approximately the same. We can also compare the standard deviations, and since the largest group standard deviation of 8.12 is not more than double the smallest standard deviation of 7.08, we can assume the variances of the groups to be approximately equal. And we can also plot histograms to see if our data meets the normality assumption. So from these, we can see that the data is approximately normally distributed within each group. So we now know that all of the assumptions have been met, and we can proceed with ANOVA, the parametric test. So we conduct a one-way ANOVA and calculate our F statistic. We can do this by hand or by using statistical software. These are the results from using R. So the F statistic is calculated by dividing the between group variation, also known as the mean squared between, by the within group variation, the mean squared error. Our mean squared between 810.1 divided by our mean squared within 59.1 gives us an F value of 13.71 with an associated p-value of 0.0003. The next question was, do you reject or fail to reject the null hypothesis? Since our p-value is less than 0.05, we reject the null hypothesis and conclude that we have evidence to believe that at least one of the group means is different. But which of the group means are different? To determine which groups are different, we can conduct pairwise comparisons with the adjusted significance levels using tests like Bonferroni's or Tukey's tests. Since we have 3 groups being compared, we have 3 comparisons in total. Remember that this is determined by the formula k times k minus 1 divided by 2. Our adjusted significance level is our alpha divided by the number of comparisons. So 0.05 divided by 3, which equals 0.017. This output shows the p-values for each of our 3 pairwise comparisons using Bonferroni's tests. We can see that when we compare the low and moderate groups, the p-value is greater than our adjusted significance level of 0.017. This suggests that there is no difference in the mean BDI between the low and moderate groups. But when we look at the p-values for the other 2 comparisons, both p-values are less than 0.017. This suggests that there's a significant difference between the low dose and placebo groups, and a significant difference in the mean BDI between the moderate dose and placebo groups. In the output for Bonferroni's, we're only given p-values for the group comparisons. To determine which is higher or lower, we can just compare the mean differences for each set of the 2 groups being compared, or we can plot the mean difference with 95% confidence intervals. We can see that the 95% confidence interval for the mean difference for the moderate versus low group crosses 0, which suggests no difference in the means of these groups. But for the placebo versus low and placebo versus moderate comparisons, the 95% confidence intervals for the differences do not cross 0, suggesting a significant difference in the means for each of these comparisons. If we use Tukey's tests, we get similar findings to Bonferroni's. So there's no difference between low and moderate, but significant differences between low and placebo, as well as moderate and placebo. But we also get some additional information telling us which group is higher or lower in our output. So we can see that, for example, the mean depression score for the placebo group is 17 points higher on average than the mean of the low dose group, and 22 points higher than the mean of the moderate dose group. But there are non-significant differences between the low and moderate groups. The confidence interval includes 0, and our p-value is greater than our adjusted significance level of 0.017. So based on all of this information, does it look like the drug alleviates depression? And which dose would you suggest? Using both Bonferroni's test and Tukey's test to correct for multiple comparisons, we conclude that the drug appears to help alleviate depression, as the mean BDI score of both the low and moderate groups are significantly different than and lower than the placebo. However, as there is no significant difference between taking a low or moderate dose, a low dose would be recommended in this case. Let's try another example problem. A research study was conducted to examine the differences between older and younger adults on perceived life satisfaction. A pilot study was conducted to examine this hypothesis. 25 older adults over the age of 70 and 28 younger adults between 20 and 30 were randomly and independently selected and given a life satisfaction test. Scores on the measure range from 0 to 60, with high scores indicative of high life satisfaction. Determine whether there is in fact a difference in life satisfaction between the two groups. The null hypothesis is that the mean life satisfaction scores of the two age groups are equal. The alternative is that the mean life satisfaction scores of each of the two groups are not equal. We know that our explanatory variable is qualitative with 2 levels, and our outcome is quantitative. We also know that the two groups are independent, they contain completely different people, so in this case, which parametric test should we use if our assumptions are met? The two samples t-test. Does our data meet the assumptions for a two-sample t-test? And should this be a t-test with equal or non-equal variances? So we know that the selection of the sample was obtained through a simple random sample from reviewing the study design. We also know from the study design that individual observations are independent and that the groups are independent. But what about the normality and equal variance assumptions? We can see from the box plots that the data in each of the age groups compared are approximately normally distributed. Plus, the sample size in each of the groups is over 20, so it's safe to assume the observations within those groups are approximately normally distributed. Should this be a two-sample t-test assuming equal or non-equal variance? Since the standard deviation of the young group is not more than double the old group, we can assume the variances of these groups are approximately equal to each other. So we meet all of the assumptions necessary for the two-sample t-test with equal variances. So we can proceed with a two-sample t-test with equal variances in R, and we see based on our output that the t-statistic is 4.83 with an associated p-value of 0.0001. Since this p-value is less than our significance level of 0.05, we reject the null hypothesis and have evidence to believe that there is a difference in life satisfaction between older and younger adults. Based on our results, older adults appear to have higher average life satisfaction than younger adults. We'll then want to interpret the 95% confidence interval and p-value. Our 95% confidence interval is 9.81 to 24.74. And our p-value is 0.0001. Our 95% confidence interval interpretation is that we are 95% confident that the true mean life satisfaction score among older adults is somewhere between 9.81 and 24.74 points higher than younger adults. Or we can switch this and say we are 95% confident that the true mean life satisfaction score among younger adults is somewhere between 9.81 and 24.74 points lower than older adults. Our p-value interpretation is, given that the null hypothesis is true, that the mean life satisfaction scores of the younger and older age groups are equal, there is a probability of 0.01% of observing the difference in life satisfaction between these groups, or a difference more extreme merely by chance. So in other words, given that the null hypothesis is true, we would expect to see the difference in the group means we observed, or more extreme, 0.01% of the time. The next part of the question is, if the mean life satisfaction score among older adults was 31.22 instead of 46.82, how would this change the t-statistic and p-value, and what would you conclude? And recall that the mean life satisfaction score of younger adults is 29.55. Since our t-value is largely determined by subtracting our two scores, or means, a smaller difference in scores means a lower t-value. In this case, if the mean of older adults is 31.22 instead of 46.82, the difference in means between the younger and older groups would be smaller. So this would give us a smaller t-value. A smaller t-value is a less extreme statistic, so it is more likely that we would observe this difference in groups merely by chance. In other words, our p-value would increase. And finally, what would you conclude? We don't have the exact p-value, but if you took the above information and calculated it, you would be more likely to find that it was greater than 0.05. So we would be more likely to fail to reject our null hypothesis and conclude that we don't have sufficient evidence to believe that there are differences in mean life satisfaction scores between younger and older age groups. Here's another example. Researchers wanted to compare two types of diets on adolescents with similar body compositions and levels of physical activity. The data consists of measures of daily caloric intake for random and independent samples of 10 adolescents on diet A and 15 adolescents on diet B. Conduct a hypothesis test at a significance level of 0.05. So our null hypothesis for a parametric test is that the mean caloric intake of adolescents on diet A equals that of those on diet B. And our alternative hypothesis would be that these are different. But as you'll see, our data don't meet the assumptions for the parametric test, so instead we use a non-parametric test and compare medians. Our outcome is quantitative, and our explanatory variable is a qualitative variable with two independent groups being compared, so we would conduct a two-sample t-test here if our assumptions are met. We know from the study description that the individuals are randomly and independently selected and that the groups are independent. But if we check the normality assumption with QQ plots for group A and B, we can see that neither of these follow a straight diagonal line. They should follow a straight diagonal line if the data in each group are normally distributed. So if we review our assumptions, we can see that we have a simple random sample and meet assumptions of independence of groups and observations, but we do not meet the assumption of normality. This assumption is violated. We don't have box plots or information on the standard deviations of the two groups, so we don't know if the equal variance assumption is met here, but because our data are not normally distributed, the assumptions for a two-sample t-test aren't met. So in this case, we would instead use the non-parametric alternative to a two-sample t-test, a Wilcoxon rank sum test. If we conduct this test in R, we'll get a W statistic of 112 with an associated p-value of 0.07. Since our p-value of 0.07 is greater than our alpha of 0.05, we fail to reject the null hypothesis and conclude that we do not have enough evidence to believe that there is a difference in median caloric intake of adolescents in diet A and diet B. So that's all I have for this tutorial. In our next tutorial, we'll talk about the chi-square test and how we can estimate the direction and strength of association using the relative difference, number needed to treat, relative risk, and odds ratio.